bad typo. That was supposed to be IK. Before I had it, this was I. Okay, so that's SAG. Okay, the idea is to allow every function to communicate an estimate of the gradient and keep a running average of that estimate. Just change one estimated gradient at every step. And SAG has some very nice theory associated with it. It's part of the reason why I think this idea was very influential, is because there was very strong theory associated with SAG, far beyond what you can get with regular stochastic gradient, even though they're, transparently, this is just as cheap, and it's actually not that much more complicated than just stochastic gradient. So we're going to look at two different settings, one in which every function fi is smooth and has a Lipschitz gradient. This is kind of like the analogous setting to Lipschitz gradient for all of f, where we know that f gets a 1 over k rate. We're going to ask how does SAG do in that regime, and we're going to denote by x bar superscript k the average iterate after k minus 1 steps. Now this is kind of a theoretical device. You wouldn't really keep this. Instead, you would keep the best, the iterate with the best criterion value, just like you would in stochastic gradient, for example. And how well this does is going to be an upper bound for how well the best one does. Okay, so this is just easier to make statements about theoretically. So here's the theorem. It's from that SAG paper. With a fixed step size, if we were to fix the step size to be 1 over 16 times the Lipschitz constant, and we were to initialize like this, this is supposed to say G. I think I just typed Y for no reason. If initialize according to the gradient estimates by just my initial gradients of my functions at the point x0 minus their average. So this is a centered version of this update, of this initialization. Okay, so this initialization is just initialize all the gradients at their actual gradients at the point x0. This is just subtracting off the average from all those, right? Because f is the average of the fi's. You could also initialize at 0. If you initialize at 0, very similar bound holes. Okay, so the theory applies to both. This one is just simpler to state, which is why I put it up on the slide. So for this initialization, after k iterations, the expected suboptimality of SAG is bounded by the following. This term is very much like what we have in gradient descent. Okay, in gradient descent, just to remind you, it's actually L over 2k times this exact same term for full gradient descent, where we were began minus the optimal point distance from those two squared. This is something else, but it still goes down like 1 over k. So this is actually the difference in criterion functions. Okay, f at the initial point minus f star still goes down like 1 over k. And the expectation here is taken over the random choice of index at every iteration, just to remind you of that. Okay, so that's the theorem. Let's again kind of distill it down, make some comments about it. As I said, it's stated in terms of the average iterate. This can also be shown to be true for the best iterate we've seen so far. So you would never really be taking averages of the point in practice. You'd be keeping track of the point with the best criterion value. That's this guy here, xk best. And so this same result also applies to xk best under kind of very minor additional assumptions. What we saw there is that was a 1 over k convergence rate for SAG. Okay, this is very different from what we get for stochastic gradient, which remember was 1 over the square root of k. And it's on the same order as what we get for full gradient descent, 1 over k. Okay, but SAG is, again, it's just, if for example, the optimization problem is p-dimensional, SAG updates are order p, stochastic gradient updates are order p, full gradient updates are order np. So they're very, very different iteration costs. One important point, which is what the authors, they make some comments about, but I think it's actually, I thought this was actually quite surprising when I read some of the details of their analysis, is that the constants are very different for the SAG bound and what we get for gradient descent and stochastic gradient. So here I've put down, roughly speaking, the bounds that you can derive for these three different methods in comparison after k steps. So for sag, we get the following. It's 128 times the Lipschitz constant over k times the square distance from optimality. For full gradient, so that's only this one term here. I'm going to ignore this term in a second, come back to it. For full gradient descent, it's the Lipschitz constant over 2k times the same thing, square distance to optimality. So we actually proved this one in class. To remind you, we just wrote it by 1 over 2 times k times t, where t was the step size. But if you take the step size to be 1 over L, which is the biggest you can take it to be constant, this is the bound we got. OK, so the 128 and 2, that's not what I'm talking about. Those, I guess you could consider those different, but that's not really what I'm referring to. I'm going to get back to the first term. That's the difference. In stochastic gradient, this is not a real bound. This is a loose translation of the bounds you get with stochastic gradient. But this is the best kind of comparison I could make. It's like L times some constants over the square root of k times the distance to optimality. OK, so those are the bounds we get for the various methods. But look up here now. Sag actually has a first term. This first term depends on n. OK, so that can be very large when n is very large. Now, this is not saying that sag has an expensive iteration complexity. Remember, this has nothing to do with how expensive each iteration is. Each iteration is still order p if the optimization variable is in p dimensions. This is saying that the bound that we got with sag, one of the terms in the bound can actually be quite large. So it is order 1 over k, but we have this pesky factor of n here. OK, so that's potentially problematic if we're comparing these bounds. Now, there's a few points to be made about this, and the authors have just a small discussion. First of all, that n is multiplying the difference in criterion values at initialization and at optimality. And if you intelligently started off sag, so if you start off sag at a point x0 for which that was small, then you could maybe mitigate the effect of that first term. You can make that first term quite small. For example, they even make the suggestion, if you run n stochastic gradient steps, you take the result and you plug that in to sag as the initializer, then that's not super expensive because you just run n steps of stochastic gradient. And what do we know about that first term? That first term then, by this result, should be on the order of 1 of the square root of n. So actually, we're going to get a square root of n over k dependence in the first term. It's a way to make that bound small. I don't find that super convincing. I don't know if in practice we would actually do this. I did try in the experiments that I'm going to show coming up to do this, and it didn't seem to help much. But I wanted to point out that while you will see lots of papers celebrating now these convergence rates for these fast stochastic methods, you have to be kind of cognizant of the fact that some of the constants can depend on n for the fast stochastic methods. OK, so kind of a caveat. Yeah, Kevin. This? No, it's actually not squared. Yeah, that was not a typo, even though I've made a few so far. Yeah, it's another interesting distinction. So this is not, again, an actual bound. This is not actually a bound on the expected suboptimality of fxk minus f star, but this is taking a bound derived in terms of epsilon, so epsilon notation. So if I told you I gave you an epsilon, and you asked how many steps would you need to take to get that, you can bound the expected number of steps to get a certain degree of accuracy epsilon. This is just inverting that statement. Those are how the statements are usually made for stochastic gradient. And I've inverted that statement to get this bound. And it is true that the dependence on the distance to optimality is just a distance. It's not a square distance. Han? Yeah. I didn't get the question. So if you believe that this is a bound on expectation of fxk minus f star, which it kind of roughly is, then if I were to run this for n steps, and then define x0 to be the result of that, then that first term is going to be on this order, L square root of 5 over the square root of 2 times n. And I'd plug that up in there. No, fx. These are all bounds in terms of fx. F of xk minus f star, or the expectation of that. Yeah. You only get bounds in terms of x, k minus x star under strong convexity. OK, all good questions. So how about strong convexity? So for strong convexity, we get another very nice result, which is that basically sag gets a linear convergence rate, just like full gradient does. So if in addition to the assumptions in the last slide, which was just that each of these were Lipschitz with, or had a Lipschitz gradient with constant L, if they were in addition strongly convex with parameter m, then with the same step size, the same initialization, sag gets the following bound after k steps on the expected suboptimality gap, something less than 1 to the power of k times pretty much the same term we saw here. It's almost that exact same first term we saw there, just with the factor n pulled out. OK, so let's just look at this for a second. This is 1 minus whatever is smaller, the strong convexity constant, over 16L. So this is actually quite a similar term to what we get in gradient descent. But this is new, 1 over 8 times n. So whatever of these two is smaller, to the power of k. And this here doesn't have a bad dependence. Right? This is probably on some constant order. That's on an order 1 over n or so. Okay, so we really do have it's some rho to the power of k times a constant. We can compare this to a very similar rho. So the rho for gradient descent is basically not going to have this term, but it's going to have something very similar to this term. So we also get a linear convergence rate for full gradient. And remember, I said there's only a 1 over k rate for stochastic gradient. So we have very different convergence regimes for sag and stochastic gradient. Like full gradient descent, we say that sag is adaptive to strong convexity, because if I use the same step size and the same initialization, it just does better with more assumptions. So that was an important point that we didn't really talk about when we talked about gradient descent. Gradient descent, if you have a Lipschitz gradient and you choose the step size in one way, you get this rate. If it's a strongly convex function, you don't have to change the settings for the algorithm. It just performs better. It gets a linear convergence rate with the same initialization, the same step size. We say that it's adaptive to strong convexity because it has this property. Sag is the same way. Okay, it just has a better rate with more assumptions, but you don't need to change the algorithm's settings, which is important for practical application. All right, the proof of these results is not easy. This is one of the harder proofs I think I've ever come across in optimization. It's 15 pages long, and that's the condensed version. That's the very short version, which is a computer-aided version of the proof. So at some point, they need to check positivity of some polynomials that arise. And to do that by hand, I suppose would take a lot longer. So they actually invoke symbolic solvers to check that these polynomials are positive. So the shortest version of the proof that's computer-aided is 15 pages. The longer version I don't think is in the is even online, but I'm told is much longer. So not anything we would ever cover in this class. It's also not something that people can unfortunately really learn much from. The proofs are so complicated, and at some point you get to a roadblock where you call a symbolic solver that not too much insight can be gained from those proofs. That's one of the downfalls of SAG. So okay, let's go back to our logistic regression example. After reading about all this stuff, and learning about all this stuff, you might be very excited to see how it performs. This is how it performs. I was quite disappointed with its performance. It doesn't steal the show at all in this logistic regression example. So I've just to be careful, I've actually rerun each of these stochastic methods 50 times. And what I've drawn is the result of every run as a kind of thin, transparent line in a particular color, and the thick line is the average performance. So I would have loved to have given you a picture where sag is hugging the full gradient curve as the theory predicts, but that's just not reality, not for this example. And sag is about on par with stochastic gradient descent. Maybe a little worse, but I don't think there's much to be gained from that comparison. Okay, so here are some notes. I fixed the step size for sag to be about as large as possible before it diverged. So I tried to tune them all as best as possible. I initialized the sag algorithm with all these gradient estimates at 0. So the more expensive initialization, where you actually initialize them at these guys or their standard versions, didn't help at all. It was the same for me. It didn't help to warm start it by the output of stochastic gradient. I tried that. What did help, and this was an important modification, was to reweight the earlier iterations. So this is a suggestion that the SAG authors make, is to actually only to take an average where you divide by 1 over k rather than 1 over n, because if you initialize at 0, then most of them are 0, and so you're just averaging out things that are 0, and you place too much weight on meaningless gradient estimates. So if instead you divide by k, then you're effectively just taking the average of the non-zero things. Okay, and if you were to run this for more steps, then if k gets larger than n, then you switch this back to 1 over n. But that actually did help, somewhat. So I really hope there's something I've missed. Actually, this is perplexing to me. I've put my code online. So if you go to the lecture slides, right next to the lecture slide is my code. I apologize for the fact that it's in R, but it's right there. It's if you guys can figure it out, I would be thrilled. I've actually also emailed one of the authors of the SAG paper. So that's the result. Here's the results from the SAG paper. They are better. And again, it's possible that there's some tricks in implementation that I missed that were kind of fine details. Here are some results from that paper. Each panel here is a different problem setting, and every color here is a different algorithm. The pink is SAG, and perhaps the most interesting comparison is to the blue and to the black. So black is full gradient. No, excuse me. Blue is stochastic gradient, pink is SAG, and red here is full gradient. Okay, so most of the times, SAG is beating quite handily full gradient and stochastic gradient. There are examples in which stochastic gradient and SAG perform about on par, like, for example, this problem setting. So it could be that we're just looking at a problem that's of this nature. That could be the logistic regression example that we saw happened to fall into this particular case. But most of the time, you can see that SAG performs quite a bit better than the competitors. So yeah, there's some hope there. OK, so we're almost at the end. I actually want to mention something very important, which is a different algorithm called SAGA. And I really wish I had more time to explain this one to you guys. It's very similar to SAG. It came out the year after SAG. I don't think it stands for anything. They just added an A at the end because it's similar to SAG. And it differs by one key detail, and that was kind of about what was raised earlier, which is that it weights the current gradient estimate much more heavily than the previous ones. So the same algorithm, okay, store some gradient estimates, pick one at random, all the way to the end. But instead of computing an average, you can see what I do is I actually I take the new gradient estimate, I subtract off the old one, and I average the old ones. So effectively, I'm placing much higher weight on the difference in my new gradient. SAG would have put a 1 over n term here in each of these. Okay, so just say that again. SAG, look up here. SAG uses this gradient estimate. Right? It effectively cancels out the old gradient at function ik from the average and adds the new one. SAGA places much higher weight on the newer gradient value. Okay? So that is the only difference between the two methods, SAGA and SAG. So remarkably, the SAGA estimate's unbiased. So it does not give you a biased gradient estimate. It actually gives you something that's unbiased, and it has a big reduction in variance as well, because you are including an average of many things. So the proof for that is right here on the slide. We are so short on time that I'd rather just have you look at the slide and refer to the Saga paper for that, because there's still a few more things I wanted to mention. So Saga basically matches the convergence rate of SAG. So it gets essentially the same theoretical results as what we already saw, but the proofs are much simpler. So that was the big advance in Saga. And the authors think that the reason was that SAG was so complicated was because its estimates were biased. So the gradient estimates were biased, and it took a lot of care to show that it didn't hurt you too much. SAG is very unique in the sense that among all stochastic methods, I don't think any of them use biased gradient updates. That idea has never really been looked at. Saga is like an unbiased version that has a much simpler proof. So this was a NIPS paper. The proofs were in the appendix. They were not computer aided. It was, much more normal. Another strength of Saga is that you can extend it to composite problems. So if you have a proximal, if you're thinking about applying proximal gradient descent to a problem of this form, then you can just replace the smooth part by the Saga estimate of the gradient and wrap the prox function around it that corresponds to the non-smooth part. Okay, so this is the Saga update for the smooth part, and then we're applying the prox operator. So just as you would with proximal gradient descent, just replacing this by an estimate of the gradient. This is the estimate of the gradient that we're getting from Saga. Okay, and it's not known whether Saga is generally convergent under a scheme like this one. So, yeah.
It seems desirable to not only weight more the newest iteration, but if you, for example, if you updated one gradient onto your previous iteration and there's another one that you have never updated, then it might seem like it would be desirable to give different weights to those as well.
So you're saying that I may not have touched a bunch of gradients at all, and those should have even lower weights than the ones that were updated recently. Yeah, that's an interesting idea. I don't know whether or not, I think for SVRG, I think that does something kind of similar to that. So there's many others that I'm listing soon. But I think SVRG may do something somewhat similar to that, although I'm not positive. Yeah, interesting idea. Okay, so here was the, this should be really the punchline, these plots, but they didn't quite work out as I would have expected. Again, I would have loved to have showed you, Saga like hugging the full gradient curve, but that's not what happened. It basically performs on par with stochastic gradient in this example. Okay, so it's in pink here. It's pretty much the same as stochastic gradient descent. So SAG and Saga, same iteration cost as stochastic gradient, as long as you're kind of careful about updating these averages. So there's not really a downside to use them versus stochastic gradient. It's not like they're going to be more expensive, and it's not that they perform worse, and they have better theory. So I don't see a real downside to using them compared to stochastic gradient, but they don't perform as the theory predicts, not for this particular example. They have in other examples that are in those papers, so again, there could be, maybe the setting is challenging, maybe I just missed some implementation tricks. So that was the my kind of summary of SAG and Saga. I think they're pretty exciting. I want to mention there are many, many others. There's something called SDCA, Stochastic Dual Coordinate Ascent. It came out on the same time as the SAG paper. It's actually very similar to SAG when it's written in primal form. There's SVRG, which is very similar to SAG and Saga, but it doesn't actually store the full table of gradients. It stores an average and only updates the average occasionally in an outer loop. There's also something called S2G2, MISO, Finito. There's tons of papers coming out on these fast stochastic methods. A lot of them have very good guarantees. I think that it's kind of an exciting time for fast stochastic optimization. And if you're interested in learning more, both the SAG and the Saga papers give very nice reviews and discuss lots of connections. So the SAG paper in particular, it's quite long, and it has an entire section devoted to all these different methods. And here's a table comparing some of these methods from the Saga paper. Okay, so now that we have all these new methods, you might ask, are we approaching optimality? Like, is there some point at which we also get a lower bound which tells us that we are at the best we can do for minimizing finite sums with stochastic methods? Because we thought we were there right, with some of these old results from Nemirovsky, but it turned out that actually those results applied more generally to minimizing expectations of functions that weren't necessarily just finite averages. So that's another very interesting question. And recently, Alec Agarwal and Leon Batu, they have lower bounds for minimizing finite sums, but they don't match the upper bounds that we have for SAG and SAGA. Okay, so there's one of three things that could be the case. The first is that the algorithms that we currently have are non-optimal. So that would be great. Faster algorithms out there, more NIPS papers for everybody. You know, everyone celebrates getting even better algorithms, more papers we can all write. The second possibility is that the lower bounds can be tightened. So that probably possibility is not quite as fun because that's hard and it's maybe not as exciting. The third possibility is that the upper bounds can be tightened, which again, maybe there's an algorithm there that's optimal, but we don't have a good sense for its upper bound. So this is a very active area of research, and I think it's all going to be sorted out very soon. If you're interested, then take a look at the references that I put at the end. So that was it. Thursday we'll cover non-convex stuff, and I will see you guys then.